This video will introduce you to the hexadecimal numbering system. So we already learned about, let me make this a little bigger. We already learned about base 10, which is the decimal numbering system. We learned about base 2, which is the binary numbering system. And now we're going to look at hexadecimal, which is called base 16. So that may sound harder since it's called base 16, but it's really not. Why do we need hexadecimal? First of all, hexadecimal is just a shorthand notation. It is not represented anywhere inside of your computer. Sometimes students are confused about that. It's just when we're dealing with a lot of ones and zeros, something like this, can you imagine having to rewrite or code that? And that's what they had to do back in the day. It was very long and error prone, and so they could be, just transferring again or coding on punch cards or something, and they were very likely to make a mistake because these strings of bits were just very long, and so again very error prone. So someone came up with this idea to use a sort of shorthand notation when they were talking about different bit patterns. So we use a single symbol to represent a pattern of 4 bits, and it's based on 16 characters, 0 through 9. And that's only 10 digits, and so we have to borrow some letters, A through F, for that. So here's just kind of a table of the systems that we've looked at already. So looking at patterns of 4 bits in the binary system. So let's take a look at this middle column. We have 16 unique values starting from all zeros and kind of counting up, if you will, all the way through all ones. And so again, that's 16 unique values represented there. Now, we already talked about how to convert binary to decimal for our human brains, but this is the decimal representation of these patterns of 4 bits, okay? Now, if we were talking about binary, again, and we were stringing these 4-bit patterns together in a long string, it would be very error prone. Think about having 16 digits or even 12 that we had to string together. We'll probably make a mistake. So hexadecimal or base 16 is used to just represent these bit patterns so we don't have to write the bit patterns out. So if I'm talking about, the bit pattern 1010, then I can use the shorthand capital letter A to represent that. Let's kind of see this in action. So this is the binary that I had on slide 2, the bit pattern that I had from slide 2. And so how we do that is we break it up into 4 bits, and we actually start on the right hand side. Whoops, let me try to grab just those 4. Well, it's not going to let me do it. But I start here and go right, and so 1110. If I look that up in my chart, 1110 is equivalent to E in hexadecimal. And so that those last 4 bits, that's equivalent to E. And I just keep working my way left, and I grab 4 bits. And so 0011 is equivalent to 3, 0010 is equivalent to 2, and 1010 is A. Now, I made all of my examples come out to, equivalents of 4 or multiples of 4. If I had an odd number, then anything to the left, you just fill in with preceding zeros. And so you may have that come up at some point. So we would say that the hexadecimal representation of this bit pattern is A23E. And that is much easier to remember than the bit pattern itself. If this was something that you worked with every day, you would have these things memorized in no time. You'll notice, in fact, that 0 through 9, up through this point, it's exactly the same as the decimal representation. So it's really just these 6 that you have to worry about remembering. And we're not going to be doing a lot with this in this class, but your lab today has to deal with this. So you may want to screenshot or jot this down so that you have this to look up when you're doing your graded activity for this lesson. All right, so let's do an example just so you can kind of see the wording. Convert the following hexadecimal representation to its equivalent bit pattern. So that's how you'll see it worded. and then you'll have one or more characters, hexadecimal characters here that you have to then convert into bit patterns. So what you're converting here is 1A, and notice there's a little subscript H here. You might see this in some textbooks, or if you Google it, that just represents hexadecimal notation. Because imagine if the A was an 8, and so you're seeing 1/8. Well, that looks like 18, right? But if it's written in hexadecimal, you need a way to note that. So oftentimes textbooks and websites that talk about hexadecimal, they will use this subscript H just to denote that it's written in hexadecimal. So how do we go about the conversion? Well, we need to convert the 1 and we need to convert the A, right? And so I've already looked these up on the charts, but you might know the bit pattern for 1 because you've already done some decimal to binary conversion, and so that's 0001. And then A, you might have to look that up in the chart. So I'm going to go to the chart and I'm going to find A, and that's the bit pattern for A, 1010. And so, whoops. So the bit pattern for A, 1010. So my answer would be 0001, 1010, and that's how I would write it. So again, on your activity, your graded activity for this week's lesson, you will be asked to do this. And so make sure that when you put in the fill in the blank answer, that you run them all together like this so that it will be graded correctly. All right, let's look at going the other way. Convert the following bit pattern to its hexadecimal representation. So here is a pretty long bit pattern. This has 12, and so you want to start, well, if you know it has exactly 12, you can start on either end. I usually start on this end, just in case they're not multiples of 4. So 1001 is 9, and if you go look that up in the chart, you'll see that that's 9. And then the next 4 I'm grabbing are 0011. I know that's 3. And then the last 4 that I'm grabbing, 1011. Again, you may have to look that up in the chart, but it's B. So the way you would write this then is this bit pattern is equal to B39. That would be the answer that you would type in. So why don't you practice a little bit? So you might want to get out your scratch piece of paper and try to convert this bit pattern to its hexadecimal representation. Again, it has exactly 12, so it's nice and even for you. And then here is a hexadecimal representation that you need to convert into bit patterns. And see, so here it's 73, which looks like 73, but it's not. It's written in hexadecimal, so that's how you know that you need to convert it into bit patterns. So you may want to pause the video and do that, and then I'm going to go ahead and put up the solution to those. So hopefully you got that right, and good luck on this week's assessment.